Hello everyone, this is a new workshop on the fluent meshing and the fluent solver, and the version I'm using is 2022 release 1. And the benefit of using fluent meshing is that you can create the meshing in a meshing and a solution in a single window. And the second main advantage is that you can create the mesh with a few clicks only. So for example, here I have the geometry of MN body with the dimensions, like the width is 389 millimeter and the height of body is 288 millimeter, that is from here to here, the blue color size you can see here. And the legs, that is standing over here, there's a distance between the body and the road is 50 millimeter, and the length of body is 1044 millimeter or 1.044 meter. And you can see that we have these properties, and these are required for the fluent simulation. And based on the height, which is a 0.288 meters, the Reynolds number is 768,000. But based on the length, the Reynolds number is 2.784 in 10 power 6. And after applying these sizing in the fluent meshing, which you can see over here, we ensured y plus is less than 1. And the turbulence model we use is the RKE, that is a realizable K-epsilon model with the enhanced VAWT treatment. And I use a pressure-based coupled solver with default settings. And this is a mesh. So with these three body of influences, body of influence 1, body of influence 2, and the BOI 3, you can see the mesh is progressively refined. So first it's a very refined, then second refinement, and then finally third refinement. And this is some cross-sectional view where you can see the Hexa mesh, and around the body and on the road we have the polyprisms, and between these two elements, the polyprisms and Hexa elements, we have the polyhedra elements. But on the surface we can see clearly that we have the poly elements. This is a bonding layer on the one of the front faces. And finally you can see that the convergence is very good. This is the convergence plot for the drag coefficient, and it took not more than 100 iterations to converge the data. And for this MN body case, the slant angle 25 degrees, that is the angle over here. And for this configuration with this Reynolds number, the accidental drag coefficient is 0.285. And from this very quick CFD, the drag coefficient is 0.298, and error is around 4.5%. And I want to just show you the geometry first. This is the full body, and with all the aspects, like we are given here its radius on this part, that is 100 millimeter, the slant angle 25 degrees. This is the back side, these are the 4 legs, and the height of legs is 50 millimeter, that is the distance of this body's bottom side with the road. And then I used the space claim and made the body as a half. And the second thing is that the length of the domain is standard one, that is the 8.35, and this is based on so if you multiply 1.044 with the 8, you get the 8.352, that's over here. So this is the standard value for the domain for the MN body simulation, and this length is 0.94, that is. So this is based on the recommendation from this paper, which you can see over here. Okay, so the domain size is given over here. So width of domain is 6.493 times the height, which is 0.288. And because we are using symmetric models, so its half would be equal to the 0.93499. Now in the space claim file, you can see this is equal to the 0.94. And this is because of the round-off error. So if I put the more zeros there, okay, so from the units, if I put the more zeros, you would be getting the more values over there. Okay, so 0.935, and we have the 0.93499. And if you take a look over here, this is the 0.93499, which is 0.935. And the same is the 0.935 is shown over here. And as far as the height is concerned, so in this paper, and this is based on the ERCOF-TAC workshop recommendations on the turbulence modeling. And here the height of domain is a 4.861. 4.861, which is 0.288, is a 1.399, which is 1.4. And same is the case over here, 1.4. And the domain length is also given, which is also based on those same recommendations. And in this paper, this is basically they are running the different models like the RANS and the LES, and also they have the external data for the same case. Okay, and you can see that they are quoting that from different experiments they have the drag coefficient of for 25 slant angle 0.285, 0.299 and 0.340. And the reference number 4 is the main reference, which is shown here. This is the main reference from where the M1 body case started. This is the paper which they are referring. And in this paper, they have the data at the end of this document. But that's in the graphical form. So this is the different drag coefficients. And they said that the 85% of the drag is coming from the pressure drag. That is because of the body shape and the separation. And because of the body shape, we have the separation on the rear end. And that's why we have the drag. So they are saying let me show you. So they say that a drag breakdown revealed that almost 85% of body drag is pressure drag, and most of this drag is generated at the rear end. And that's why I made a very refined mesh with the 3 body of influences or BOI, so that I can capture that value. And that's the reason that why I'm getting the results very close. Okay, so after doing that thing, you can see this is the mesh in the fluid meshing. And this is the level of the mesh. You can see over here the Y plus is less than 1. This is the boundary layer on the M1 body. This is the boundary layer on the rod. And as it is going through the body, we have the more cells in between the body and the rod. And this is based on the proximity function. And you can see that we have put the number of cells equal to 12. Okay, then after making the mesh, you can see this is the workflow type based meshing, which you just define the geometry at the sizing, generate surface mesh, and maybe improve surface mesh, describe geometry like the boundary conditions, add the prism layers or the boundary layers, and generate the volume meshing. And once you do this thing, then the next thing is that you will be solving that case, and that is also from that same window. So you have to just click on the solution, and it will take you to solution mode. And this is the case I solved already. So I want to show you that case as well. Okay, before I take you the fluent, so I was discussing about the drag coefficient, and you can see the major component is coming from the wake drag or the pressure drag. And for the 25 degrees slant angle, this is the required overall drag coefficient for this case. And this value is almost 0.285. But they have also shown in this paper that For this slant angle, they have the from other experiments, they have the 0.299, 0.384, and if you go to 34, 34 is the experiments and numerical simulation on aerodynamic body. This is a 2011 paper. So if based on that value, our CFD results are 0.298. So 0.298 minus 0.3, and they say that maybe the reason is that in the old times when they were experimenting with the ML body, the drag coefficient was 0.285. Because of that, the wind tunnel treatment was very good. That's why they could not get the accurate value of the drag coefficient. So with the new setup, they claim that they have the more accurate value for the drag coefficient. So if based on that value, and so the accuracy is 0.66%. So this simulation, the CFD, with the new experiment, the accuracy of simulation is 0.66%. Okay, so only error of the 0.66% is over there. So anyhow, whatever value we take, it doesn't matter, but the procedure is important. And then another experiment are done where the value is a 0.38. And in their simulation, in the K omega SST, they have the value as 0.328. From the ERSM, they have the 0.2804. From DS, they have the 0.4371. And then from the IDEDS, they have the 0.38. So you can also imagine that they have the error as compared to the simulations over the experiment data over here. But if you take it to the third one, you can see the IDDES has the almost same drag coefficient as from this experiment. Okay, so anyhow, this is another paper, and this is the 2012 paper, so it is also latest than the second reference. So anyhow, whatever value is, so we just made the simulation, and if I load the data file as well, and also there are two options you can get this data. One is that you enroll to the course, which we are running right now on the flow over the vehicles. We are solving the front wing with the tire for the Formula 1. We are also solving the 2021 Formula 1, full Formula 1, the Honda Civic, and we have the Toyota Corolla car, we have the Volvo truck. So these all workshops will be there. So we have the ML body, T-junction pipe. These two T-junction pipe, they are just to explain that because the majority of the problem we are solving here, they are external flows. So I just wanted to give you idea that how this fluid meshing technique can be used for internal flows. And I explained the two methods again, the watertight geometry and the fault tolerant meshing, so for internal flows as well. And then we have the Volvo truck, we have the Formula 1 front wing. There are two wings, the modified and the original. Toyota Camry car, we have the Honda Civic. So these all examples are covered in this course. The course fees is only 350 USD, and but for just this model you can get the videos, which are, we have the YouTube provided videos, and these all files with the presentation, this whole presentation, and the solution files, the meshing file, the geometry file, in just 120 USD. Okay, so let me show you the solution over here, the contours. Okay, if I change it to the banded and change the color map size to the 20, so you can see the results. So also if I include the legs, and maybe we can draw that thing on the symmetry plane as well. Okay, and just in the last, I want to display the vector plot that is on the symmetry plane with the body being shown over here. Okay, so you can see the solution like this. And because of the inflation layers, and we added the 25 inflation or prism layers, you can see the accuracy of the bond layer development on the MN body. And because of the wake region properly meshed, we can see that we are also getting this separated flow on the back of the slant very accurately. So just contact me on the WhatsApp. I have given my details on the WhatsApp on the Facebook. You can contact from there. So for this MN body workshop, the price is 120 USD with the support. You can ask me any question anytime. And you have the video files, you have the PPT files, and you have these all solved files, meshing files, geometry files. And for the full course that contains many workshops, the cost is 350 USD. Thank you.